Okay, today let's look at this cooperative graph neural networks paper by Oxford people. Okay, this is unlike most of the GNN papers I've ever seen. It's creative in some way that you can see. They use people used to study. Okay, this is graph. Let's do a say message passing paradigm to make it work, and they design something, say like, okay, these edges, if directed means like it has directions, like let me see, yeah, like this. If it's directed, like it can the this GN cooperative GN they can do is they can decide if one of the directions works or not. So say if you stand at point of this node, you will be looking at, say, um, it can listen from you, and this V can listen from U and W, and it can broadcast to U and W. So in a view that, so it established a network, it's called action network. What it does is, say, let's see, it's mentioned in the here. Yes, it says it has two-stage process. It says it has action network pi and environment network, and so this action network is actually deciding what's the action for, say, like if you want to listen or not, like if you want to broadcast or not. So says it has actions, like for actions, like it can predict standard, it's like both broadcast and listen to the neighbors who wants to listen, and who and listen to neighbors that broadcast. And listen means like, yeah, just the listen. Broadcast means it can broadcast to neighbors that listen. And isolate is like neither listen nor broadcast. This is like, okay, if you design it in this way, so like if it's passing this forward passing this action network, we will be deducing from this, we'll be reducing from this graph to, say, like, something like this. It's like we are not seeing the complete graph, which is some sort of attention mechanism that we focus on, some part of the graph, some part of this subgraph of the graph. Before, we only analyze and study given the limited information, because if you just try to squeeze everything through nodes, a lot of information will be lost or compressed in a very unhealthy way. This is basically what this model has said. Like its emphasis in multiple places about you can see about, like, it can, it's not like computed on the entire graph. It's in some way it looks at this a new structure, like some edge can be dropped. So for a layer of this graph, you can consider it as like a lesser version of this graph. Um, Something like this, like if you compute layer after layer after layer, it will be, so this node will be depend on less, like not less, it's like more focused information. It also mentioned that to learn the actions to backpropagate, so what's the action might be better, um, besides the action that I mentioned, which is the pi. I think it's like following reinforcement learning's mathematical notation. It says it's using Gumbel softmax. It's a version of softmax that we put on extra something of like a random noise. It's one of the random noise besides Gaussian and the uniform random. It's you can calculate Gumbel from uniform random, and you add it to the original softmax on denominator and numerator, and you have Gumbel softmax. Don't worry, this is a function already in PyTorch, and this the rest is environment network, which is basically the MPNN before, like a message passing neural network before. It's like they didn't inventing anything new here. They are just like saying, okay, with this new design, we can focus on some part of the graph, like in certain layer. By layer, I think it means like, if this path jump to this is like one layer. If you want to understand the information based on this, but for the next layer, say it's for V, so this is the second layer, and it basically equals the number of the hops. Like if you say it's like 2 hops, it's basically 2 layers. Okay, let's look at the code for a while, because okay, this is their on the right side. This is their official code. They have like corporate GNN. They offer it as like a anonymous GitHub repo. I don't know why they choose this instead of GitHub repo. I'm going to respect their intention of privacy. So I won't be publishing any code because it's this basic their code. I just like reshuffle some of them into one of my notebook to play with it. So you can see, if you can see here, let's make it wider. By starting of it, you can see it's been importing. Okay, then it has a lots of data sets. One of them is called Roman Empire, and this is just a toy data set. I see most of the data set, GNN data set are they're relating to biochemistry, something about like enzyme, peptides, is clearly there to play with the amino acid structure. So this is one of the model type. It has several model types. If you look at the layers, you can see there are lots of types of layers. Some like inheriting from convolution like structure. So this kind of inheriting, you can see it has already defined forward pass and the net function, and it just rewrites some part like they think necessary. And for this linear, I think it's like this is the most basic version. You can choose which part of like a layer encoding that you want to perform. So they load the data set. This is special like data loader data set like for like graph data. It's like not the usual like PyTorch data loader. If you look at them, if you get one row of the data, you can see this one. Sorry, if you get one row of the data, which is here, I think this is sample data. One row of the data. Oh, sorry. Which I think this is the entire graph. This is basically the entire graph, like and y is the target you want to predict that the function you want it to perform. And I guess this is a classification task, and you can see it has basically 22k nodes with features. This is input feature like 300. You can still define the dimension model. Here is for environment net, it's basically 64. So this is data, not relating to model structure. So you can see this is 300 is input feature, and y is the classes. If you look at this y, it's basically it's restarted. So sorry, I cannot show it anymore. Yes, this is basically the classes, I guess. So if we're looking at this as edges, it means like edges looks like this. This is like a first node, second node, first node, third node, first node, second node, first node. This is directed, means that first to second is different from second to first. This means like for each edge it has I guess so this is basically data set. So we put this thing into the network, and I break down what this network does here. If you want to, you can follow the steps of their code somehow. Like let me see what's the yeah, it's here. So what they does is, okay, so first they have this InfNet, they have this like environment net, which is not like what their paper claim. They also include the input and output of the entire model. What it does is, so here, this is the structure of InfNet, which is like translate the input dimension to the hidden dimension, and it also include the translating the hidden dimension to the output dimension. So I guess this is a classification problem set. Also, it infers the loss function from the data set. So I print it out here. Sorry, it's this. I think it's here. If you look at the metric, if you look at the task loss function, it's cross entropy. Yeah. So okay, we are using cross entropy to do a task that's like have classification on each nodes. Okay, now let's look at how this model works. First, we want to translate. This is like using we do some sort of norm. This is like doing for each of the layer. You can see it's performing layer after layer. This is the layer index. This is number of layers. So for first layer, we do hidden layer norm. But also remember this this input x can be this x from last iteration. So for each layer, it does some sort of layer norm. So after this step, we put it into the model. This model is like you can see. Like before that, like the first step is use the InfNet, like the first layer of the InfNet. Like I said, it's just translating the input features, number of input features into dimension of hidden layer features, because all the model works with the dimension is 64 not 300. So let's translate it here. You can see translate from 300 to 64 here. Then for each layer, the calculation looks like this is in logits, this is out logits, calculated by in ActNet and out ActNet. So this part is a little bit different from say like this one. So if you look at this like policy or action net, you think it's like for classes prediction, but actually it's not. It can predict, for this very specific relationship, this say, like this broadcast node and listen node, do they broadcast and do they listen? So the prediction looks a little bit, after this logics, you apply the Gumbel softmax. It does something like this. It's for each node, this is like predicting 1 or 0, 1 or 0 or 1. So if you look at this, this is basically, you can compress this into like a single dimension. You can compress it into say, so if you try to calculate the, sum of this thing for each row, you'll find the max and minimum value is 1. That means like has to be 1 0 or 0 1. So this is close to binary classification, but they're doing in 2 digits instead of 1, because like you don't need like 2 numbers to represent a Boolean value. They're using 2. I guess the reason is they're using Gumbel softmax, like for each of the row, each of the elements here. You can do about propagation. It's like this 1 or 0, it can be it can be used to back propagate to learn the action net. So this might differ. Also, the point of using Gumbel softmax is it assigns some sort of random number in the learning phase. So it's not like whatever it's like whatever is positive will stay positive or negative will stay negative. It's like it will be assigned a random number. So later on it will be learned to lean toward like either positive or negative. So instead of using argmax, we should not use argmax here, because there won't be any gradient in that way. We're using like slicing. So if you see this is 1001, if you're slicing this one, like the first column of this matrix, you can see this is basically the Boolean value that you need. So this is in probabilities. That means do we listen or not? So this node listen or not. For this, you see the shape is equal to all the nodes. So you can see this is like you want to see, okay, if this nodes listen or not, like in this situation. And this nodes, do they for each nodes, do they broadcast or not? So if you do a Cartesian product somehow, and you can basically have these four classes, this is basically Cartesian product of do you either listen or not, or broadcast or not. Okay, if you have this and you multiply them together, say not multiply these two, but if you treat this like an edge index, you split it into all the first nodes of all the edges and all the second nodes, all the receiving end of all the nodes. You will find out that if you use this as a slicing mechanism, use this as slicing, say like for each edge, where's the node? So we will be slicing out, say this is edge, all the in nodes for all the edges. This is all the out nodes for all the edges, and with the multiplication, says only in case that they are the in nodes is listening, which this position might be for the first say the position in the position of this edge, if it's 1, and also in the out position, in the out node, it's also 1. It can they can communicate to each other. That means one has to listen, one has to be capable of listening, one has to be capable of broadcasting. So that will be involved into the calculation. And if we look at this edge weights, this is basically say how many edges still exists. Say if you have directed edges, say this is the if you say the count of this edge weights, they are 1,000, and the actual ones you can count it in this vector, like a single dimension vector. Of course it's less. This ratio, so that this mean is basically the remaining number of edges compared to the original graph. It's how many of the edges still exist in this subgraph that we are trying to focus on. You can try to use that to do some visualization if you want to, but this is the main idea how it does it. And after you calculate for each layer, which kind of edges you want to make them stay, you just iterate through the middle 3 layers of nth net. So for the first layer, you only use the first layer. So here you can see besides the this 0 layer, you wanted to only use one of them as forward pass to calculate this out. After some activation, dropout, you can see this is basically how you update this node. So this is basically how they are doing this cooperative network, cooperative GNN. You can see they still write their own training iterations loops. People still doing that. I don't understand why, but yeah. Also, I think this is has some expressive value that you can say if you want to visualize what part of the supergraph it has. You can still do that. If you have this graph, you have it visualized, if you want to see in each layer how does it work, how does it like truncate or like trim out uh, the edges that they don't need, you can still visualize them using the edge weights that I talked about. Yeah, have fun.